This is an agent-based epidemic modeling. In the simulations, we will see the influence of travel ban and social distancing before, during, and after the ban in the community level. First, let us see what an agent-based model looks like. Past researchers mostly looked into international level travel ban, not the community level ban. Partial travel bans helps in slowing down the spread when global number of cases is low. Mathematical models do not support travel ban when the pathogen is very contagious. We need social distancing with the travel ban for an effective containment of the pathogen. Traditional SR model has some limitations. We cannot add traveler to the SR model. There is no second wave in SR model. The goal for these simulations is to see the effectiveness of travel ban with social distancing in slowing down the spread of a disease. We also want to see the effect of lifting travel ban early in the community. By varying variables in the model, we want to get different scenarios for a community during pandemic. We will run the model in a system that has 700 local agents. Social interaction decreases by one third than normal time during travel ban. A traveler may be connected with one or more local agents. A few people will leave after the ban from the system. We will change lifting and imposing days for travel ban in this model. Let us see some simulations now. In the first part, no locals are affected by the pathogen strain initially. In this simulation, travel ban is implemented from day 7 and lifted at day 49. A traveler has free connection when he or she enters the system. If you see the left side graph, highest infected number were found before day 75. Susceptible and recover lines cross over at day 70. In the right side graph, number of asymptomatic and contagious people starts to decrease after day 70. The graph flattens after day 75. Here, number of local infected people were 502 out of 700. Here, we are using the previous template only with one change. A traveler has only one connection with the local agent when he or she enters the system. Local infected number is 511. In this part, some locals are affected by the pathogen strain initially. In the simulation, if you see the graphs, you will find a second wave of infection, which is not found in the traditional SIR model. The infection rate is a little bit lower in the simulation. Total local infected people is 486 in this simulation. In this simulation, travel ban was implemented from day 7 and lifted at a later day, in this case at the day 200. From the graphs, you will see infection rate rises after a delay, so travel ban with effective social distancing can slow down the spread in a community. Let us discuss the results of the simulations. By changing variables, we found different scenarios in the community. When no locals are infected and travel ban is lifted early, we found connection numbers do not matter in the final local infected tally. Delay lifting of travel ban with social distancing slows down the spread of the pathogen in the community. So, what are some limitations of this model? This is a probabilistic model, not a deterministic model, and more people need to leave the system during simulations. Right now, approximately 2% people leave the system during simulations. This is not a high number, so this needs to be addressed in the future. This is the reference list, and thank you for watching.